So this is our third lecture on Exergy. We've talked about Exergy as a property for a closed system, and also the flow Exergy for an open system. Now, you have the Exergy balance equation, just like you have a mass balance, just like you have an energy balance, just like you have an entropy balance. Now you have a fourth Exergy balance. You can apply it to a closed system, an open system. I know that was a lot to review. We did it last time. I put up a matrix 2 by 2 to help you in that. But this is our rate equation for Exergy. It's an Exergy rate balance equation for a control volume. Exergy is a property that we can keep tabs on. We can do a balance on it. So it's extremely rare, i.e. I've never had a problem over a number of years where the Exergy accumulated or depleted in the control volume. But you can develop, and the book does develop, the most general Exergy balance equation. That would be important if it was a transient analysis. All of our analyses are going to be steady state, so you don't have any accumulation or depletion of Exergy in the control volume. But there's the more general term. Then you could have Exergy transfer with heat transfer. Maybe sometimes you put a dot on it, say, hey, it's a rate. Sometimes you leave it off. You just have to be cautious of what we're describing. Because this has a dot on it, maybe we leave a dot right there. So it's a rate of heat transfer, and then we have a simpler expression for it. That's the rate of Exergy transfer with the heat transfer. And then we looked at this multiplier in parentheses. What did that look like? Carnot efficiency. Carnot efficiency. 1 minus T low over T high. So it's some percentage. So if I'm transferring 1 kilowatt of heat, maybe only 0.3 of it is the rate at which Exergy is transferred with that heat transfer. Then we had the shaft work in or out, and there's a 1 right in front of there. It's 100%. It's 1 to 1. So if I have shaft power out of 2 kilowatts, the rate of Exergy transfer with that shaft power is 2 kilowatts. This term is put in there again for in general, but look at, if we're going to do steady state, that term is 0, 2. If you had a transient problem, which you won't have one, in which the volume of the control volumes changing with time, increasing or decreasing with time, that term is non-zero and needs to be included. But believe me, steady state is what we want to master. So this term is 0. All right, then we had the flow of Exergy in with the mass and the flow of Exergy out with the mass. And notice that's our property, the flow Exergy. And then we had that Exergy could be lost or destroyed. And so it's a negative times the Exergy destruction rate. There's our Exergy balance equation. Hopefully we can read that equation. True? What do the terms mean? So when it's steady state, 1 inlet, 1 outlet, that mass flow rate's the same. So we can combine, just drop the subscript on m dot. So you find that you have a change in the flow Exergy. The fluid stream is either increasing or decreasing in Exergy as it flows through the control volume. And then this is power in or out, and then the Exergy transfer with the heat. And Exergy could be destroyed. Why would Exergy be destroyed? Because of irreversibilities, just irreversibilities, all right? So, and then the simple equation for, if you already know the rate of entropy production in the control volume, you would multiply that by, hey, I forgot, what is T naught? The dead state temperature, and it's a very simple relationship. So 1-to-1 correspondence. Like if I have irreversibilities, I'm going to have some entropy production. I'm going to have some destruction of Exergy. All right. Can sigma dot be negative? No. Can the rate of Exergy destruction be negative? Meaning you could have Exergy production. No. No. That's right. So this is no. Okay. Let's press forward. This is the derivation for that Exergy balance equation. How do we do it? This possibly, hopefully, looks a little familiar to you. You saw that in Thermo 1 when you went from a control mass to a control volume, and you went from U to H. You said, we need a new property called enthalpy when we have fluid flow in and out of our control volume. Well, how did you do that analysis? It's the same pattern here for Exergy. So what you have is you have a deforming control mass. We have confidence in our balance equation for control mass, so we start there, and then we have it deforming. And then we focus on a region, this volume right in here, that region, where it's being pushed in on one side, the inlet side, and being pushed out the exit side. So the control mass is deforming, and then we write the balance equation for control mass, do the algebra, manipulate, divide by delta t, turn it into a rate equation, and we're done. So here it is. What is this equation to start with? This is Exergy. Exergy at the initial state 1, but instead of calling it state 1, we'll put a subscript t because we're thinking about it at time t. And then at the final state 2, we're thinking that final state's happening a little in the future time, t plus delta t. What happens is you have a little transfer of heat, because this is a small delta t. You have a little transfer of heat. With it, in comes some Exergy by that equation. We have a control volume, a little transfer of work out of that control volume. You have a little work associated with pushing the fluid in and out. Think about a little piston, imaginary piston, pushing that fluid in, and a little piston being pushed back as some fluid flows out. Those are those two boundary work terms. You also want to get rid of, subtract off, or take into account the pushing back the atmosphere at constant pressure P naught, which is not needed. So this is P naught V delta T plus delta T minus V naught. This is probably the hardest term to really wrap your head around, but and then you have that Exergy destruction. So a small amount of entropy production multiplied by T naught gives you the entropy production. Exergy destruction. All right. So now you expand out this Exergy term. You say, well, the system looks like this with a little bit about ready to come in. And at the end, it looks like this with a little bit that went out. And so you say, well, it's what's in the round part plus what went out minus what was in the round part minus what comes in. And then the rest of these terms are just copied over. And then we expand those volumes, these two volumes. The CV, the round part doesn't change with respect to time, so they cancel. But now I have some almost insightful grouping of terms. So what you have is you have the mass times the Exergy exit, the mass times the Exergy exit, and then you bring with it a pressure times a specific volume, because if you multiply that mass times the specific volume, you get back to the volume exiting. Likewise here for that's an exit, and then the P naught, where did that, oh, P naught volume exit right there. And I got to scoot down a little bit. And you do the same thing in group terms on the mass coming in. Okay, we have this E plus PV minus P naught V. Expand out that E, that's U minus U naught, P naught V minus V naught, minus T naught S minus S naught. You have the kinetic potential energy terms. Then you add to it the PV. You subtract P naught V naught. You notice that the P naught V naught and this P naught V naught cancel. That this U plus PV turns into H. And that this U naught, P naught, V naught turns into minus H naught. And voila. I'm trying to do it as less painfully as possible, but there it is. All right. You then divide the equation through by delta t. Let the limit as delta t goes to 0. So what is del Q over delta t limit as delta t goes to 0? Hey, you're dividing by 0. That's got to go to infinity. That was before you took Calculus 1. Remember that in calculus? You say, let's see, I have f at x plus delta x minus the function at x, and I'm going to divide by delta x, and then they said, take the limit as delta x goes to 0. What do you get? You said, I'm smart. I learned you can't divide by 0, and you're going to 0, and so this goes off to infinity and is not defined. That's not true. You learned in calculus. That is equal to df dx. And so that's my engineering way of kind of saying this is equal to q dot. And then likewise, you get w dot, and likewise, you get m dot. And so this is our nice typed out equation. What is QED? Latin for what I wanted to demonstrate, I've now shown. It means some words, quoto estum demonstratum. I don't know. All the mathematicians put that up for years at the end of a proof, and I said, huh? What's QED? I mean, see, they ended. They're stopped. Okay, what you set out to show has now been shown. So there you go. Thank you. Solve a problem. It's very similar to the homework problem. Oh, I forgot to mention, she just left. Anything now is late. Anybody still holding on to homework? If you are, you're late. Right? Okay. All right. Let's continue on. You solved a problem like this for the homework, true? Yeah. So, should I spend time on it or keep going? Vote up or down. Yes, spend time. Okay, down. Let's move on. Okay, we got to go by majority rule. That's how we got our last president. He's going to inaugurate in how many days? How many days is he going to be? All right, so what you have is you have a wall. And the wall, they say you have a temperature here, and then you have the air on the inside, and you have a temperature for that, and you have the air on the outside, and you have the temperature there. So what you end up with is 4 temperatures. You end up with a temperature of 125 degrees C. You end up with a temperature of 115 degrees C. You end up with a temperature of 35 degrees C. And you end up with a temperature of 25 degrees C. Those are all in degrees C. You can add 273 and you got it. A lot of times the engineers, we like to, what temperature are we talking about? Why not call this 1? Why not call this 2? Why not call this 3? Why not call that 4? So we number our temperatures. You can give them more sophisticated subscripts if you want, but T1, T2, T3, T4. Notice that this is on the edge of the wall right there, at 2 and 3. Okay. They want you, given that the dead state temperature is 25 degrees C, add 273, that's 298 Kelvin. And the dead state temp pressure is 100 kilopascal, which is not needed for this problem. Somebody may say, oh, professor, they gave us some piece of information in the problem, but I never used it. You ran across that yet? You should have. The sky was blue on the day that this it's irrelevant. It's okay to have irrelevant information in the problem statement. I know it in statics and in some of the lower physics classes, it's really hard to grapple with because it seems like if they took the time to put that information in the problem statement, it must be essential. I must need it. But here's a case where, nope, not needed. All right. So what is the exergy destruction in the wall from the inside wall surface to the outside? We introduce a control volume like that. And I know that you could just say there's no mass cutting across it. Why don't you introduce a control mass? Same thing. But it's a focused, we have clearly identified the region of study for the calculation that we're going to make. Now we're going to do an exergy balance on that region, that control volume, and it's steady state. And we're going to have the flow of exergy coming in at 2, and we have the flow of exergy going out at 3, and we have the destruction of exergy. And what are we asked to solve for? This term, the rate of exergy destruction inside. So we have that the rate of exergy destruction inside is how much is coming in with 2 and how much is leaving at 3. What's my equation for what's coming in Well, first of all, how much was flowing through? Q dot was constant at 1200 watts. Let me ask you this. What is the flow of heat across the boundary at 2? Is it 1200 watts? What is the flow of heat going out the other side? Is it 1200 watts? It is. Somebody says, well, you're clairvoyant. How did you deduce that? How do you know that? I'm lost. I don't understand why that's true. Energy balance, steady state, and you can prove it. All right. So now that we know that the Q dot coming in is the same as the Q dot going out, really what I need to know is how do I calculate the rate of exergy transfer with that Q dot coming in? And it's going to be 1 minus T 0 divided by T B at 2. Why did I put the B in there? Just to emphasize it's a boundary. 2 is a boundary. And when I look back at my other equation right here, there is a B on that. So I really need the boundary temperature, which is the boundary temperature 2. So I'm a little redundant actually on the subscripts. And then we have minus, then we have 1 minus T naught divided by TB3. And at this point, I'm going to say that you can make that calculation. All right, what will the answer be? So many, what are the units on the answer for part A? Watts, exactly. It's watts. Hey, that's the same units as rate of heat transfer. Yep. You're exactly right. If I look in my notes, I could probably find the answer. 240. All right. Now, for part B, what is the exergy destruction in an enlarged control volume where you go from the inside air to the outside air? Well, just enlarge the control volume. And now I have the flow of exergy. So exergy destruction is going to be this exergy flowing in with the heat at 1 minus the rate of exergy flow with the heat at 4. And so this is going to be 1 minus T naught over T1, all multiplying Q dot, minus 1 minus T naught over T4, Q dot. Now, if you solved a similar problem, what's startling? Either something about that term or that term. What's startling to you when you first do this? The second term, right. What was the like, aha, what? What did I just do? What is startling about this term right here?
0.
It's 0. This is one of those examples where there's a lot of heat transfer, 1200 watts, but the potential for that energy transfer to be converted into work, 0. There's no exergy transfer with that heat. It's a lot of hot air, right? There you go. So this one we find that because of its enlarged control volume, you find a little larger, like 302 watts for the rate of exergy destruction. All right? All right. Press forward. We solved this problem last time, but I changed up some numbers. So I changed up that it's 3.25 kilograms per second. Why? Just to trip you up. And then the steam comes in at 80 bar 440 C, and it goes out at 20 kilopascals. So the pressure, temperature, and the pressure didn't change. But the isotropic turbine efficiency I changed to 70%. Do you remember this problem? Yeah, we were working it last time. So then you have part A, what is the power out of the turbine? Part B, what is the entropy production rate in the turbine? And part C, what is the exergy destruction rate in the turbine? 3 parts, and even they tell you what units. Do those units look pretty good for these questions? Kilowatts, kilowatts per Kelvin, and kilowatts? Sure. They give us the dead state temperature and pressure, ignored effects of motion and that. And last time I said, let's set it up where you have a nice table, and maybe you put state 1, 2, I'm going to do 2S and 2 actual. And then you have different properties like pressure, temperature, enthalpy, entropy are the big ones. We could do more. And state 1 came in at 80 bar. You could put the bar over here. And then it was 20 kilopascal, which is, how many bar is 20 kilopascal? 0.2, 0.2, right? Thumbs up if you agree. How many people don't have thumbs? All right. Temperature, 440 degrees C. What's the temperature out? Temperature out, we'll work on that. It's not given in the problem statement. What about the enthalpy? Well, from knowing T and P, we deduced it's superheated steam. And from the something principle, state principle, we get our enthalpy and entropy. So we get the H1 and S1. Now, how do we get the state 2S? We actually can think about a property diagram like a temperature entropy diagram. This is one for steam drawn to scale. It's produced using software called REF REFPROP. It's put out by your federal government, National Institute of Standards and Technology. They're Boulder, I think, Colorado office. You can purchase it professionally, or you as a student, you can download a pretty good version with a lot of steam properties in all the steam properties. But the professional will allow you to do so many other fluids. So you can generate the diagram. This is our 8 megapascal or 80 bar pressure. So this is a line of constant pressure in our diagram. What is this dome shape? That's the two-phase region. What is the name of the point at the top of the dome? Critical point? I thought some people said yawn point. Yawn point. No. Critical point. What is our temperature? Around 440. You come over right there. Guess where state 1 is on our diagram? It's superheated vapor. State 2, straight down, you do a reversible expansion, isentropic flow through the turbine, and state 2S will be right there. But because they said it was isotropic efficiency of 70%, state 2 actual with a dashed line will be somewhere like that. Why do they put a dashed line on the property diagram like a TS diagram? Because it emphasizes that it's an irreversible process. What does a solid line look like or indicate on a property diagram? Reversible. Reversible. So what we do is we jump back and forth so that you've done this. This is all just thermo 1. So this value gives us S2. Knowing S2 and P2, we can get H2. And we'll call that H2S. Assuming isentropic expansion from 1. We then calculate the work of the turbine isentropic, H1 minus H2S. H1 minus H2S. You want to find the work actual. What do? You multiply by the isentropic efficiency. So if I get 70% of that, I get 70% of it. True? This is isentropic efficiency of the turbine. So now, knowing that, I can get the actual enthalpy, H1 minus WTA. Is this music to your ears or confusion? Music to your ears. Good. And so now we can get H2A. What are the two properties that fix state 2A? Enthalpy and pressure. Where before it was entropy and pressure. Little confusing, right, when you did it in thermo 1. But doable, all doable. And you can actually then get S2 actual. Not where S2 is equal to S1. Okay. So the power out would be you multiply W dot T is equal to the mass flow rate times WTA, this answer right there. And for this problem, For this numbers, the power out was around 2501 kilowatts. Don't box that. I changed numbers from last time. What about the entropy production rate in the turbine? Are they asking me to calculate sigma dot? Is that what I'm asked to solve for? Yeah. It looks like I'm putting you all to sleep. Are you with me? It's hard work to get anything out of a 50-minute lecture. I think some faculty do a pretty good job of putting us to sleep. True? And so this sigma dot comes out to be 3.217 kilowatts per Kelvin. Now, what is part C? Finally, something new out of chapter 7. What is the exergy destruction rate in the turbine? But you had to do so much work. You had to do 90% of the work to get part A, then only about 8% of the work to get part B, and about 2% of the work for this problem to get answer for part C. Because E dot D, can it really be as simple as T naught times sigma dot? Yeah, it can. And so the exergy destruction rate comes in at 959 kilowatts. Let's do this. Let's press forward. Let's talk about exergetic efficiency of a device known as a turbine. Have you been introduced to, in the previous class, an efficiency for the turbine? Yes or no? Yes, it was known as the what efficiency? What is your isentropic efficiency? So we typically had a symbol like this, and that was our isentropic efficiency of the turbine. What was it defined as? What was it defined as? Kind of like what the work out of the turbine actual compared to if it would have been isentropic expansion through the turbine. And then you say, well, let's put that in terms of enthalpies. Sure, that would be H1 minus H2 divided by H1 minus H2S. But now we have another new efficiency. We could call it the exergetic efficiency. We could call it the second law efficiency, and we have to have a different symbol, and it won't be exactly the same in answer, in numeric value, for the same conditions of our turbine. The exergetic efficiency of the turbine is defined just like something like numerator is going to be smaller than the denominator. Numerator is going to be close. You want it to get as close as you can to your goal. So what do you really want out of the turbine, and what do you really put into the turbine to make it work? And so the answer to something like that, what you desire over what's required, or what you want over the input, was that you're taking the fluid stream and it's coming in with the high potential to do work, and it's leaving with a lower potential to do work. So something's coming out of the fluid stream, and you want as much of that which is coming out of the fluid stream to go to turn the shaft. From an exergy balance equation, what comes out of the fluid stream can go into two places: the shaft power or being destroyed. Where did this equation come from, Professor? All these new equations. Where did it come from? I'm lost. Where did this equation right here come from? Steady state. No Q dot. One inlet, one outlet. You mean all the way like back here? Yeah, that's it, right here. Steady state, no heat transfer. One fluid in, one fluid out. All we did was put this on the other side. That makes everything positive in the equation. And then you can read the equation and say what comes out of the fluid stream either goes into turning the shaft which you want, or is destroyed due to irreversibilities. So this is a good equation. You could rewrite that because you see that, well, what comes into the shaft, W dot, isn't that also equal to M dot EF1 minus EF2 minus E dot D S destruction? Sure. And if you did that, you would have 1 minus the rate of exergy destruction divided by M dot EF1 minus EF2. There's no difference in those equations, but it may be more convenient to use one or the other. Professor, this is a lot to memorize. No, it's not. Hopefully this all makes sense. Let's press forward. So go back to the same problem we just did, and now, even though the isentropic efficiency is 70%, they ask for part D to calculate the exergetic efficiency of the turbine, and how would you calculate it? And yes, it will be close to 70%, but it won't be spot on the same number because it's a different definition. How would you calculate it for this problem? We just outlined those equations, didn't we? Yeah, and when you do the calculation, I can just repeat the equations I just had. What you'll find is that the isotropic 70%, and the second law efficiency for the turbine is around 72%. All right? All right. What about a compressor? How many people remember reading the chapter, portion of the chapter where it already talked about these second law efficiency for the turbine? Any show of hands? Did we have any homework problem that required it? We will next time then, okay? And then how about for the compressor? Without looking at an equation sheet, can you deduce it? I'm going to stop, pause, walk around, 5 minutes. Try to get the equation for the second law efficiency, the exergetic efficiency for a compressor, which would be the same as for a pump. Okay? It's going to be a ratio of what? Something over the other. Can you describe it in words? What's the ratio? What's in the numerator? What's in the denominator? Yeah, I want to see you do it without the equation sheet and just right now. So what we do is, the purpose is we know that this is going to be negative and you're trying to increase the flow exergy of the fluid stream. You want that EF2 to come out greater than EF1. That's the purpose of a pump or compressor. So what you're going to put in, not all of it is going to go there, but that's the in. And I like to maybe put a minus sign on that, and so I know that it's a negative, something I expect to be negative, or make it positive. I want something positive down there. And then I can have the mass flow rate of the stream, EF2 minus EF1. Now some people put M dot EF1 minus EF2 divided by W dot, meaning that this term is negative, but also that difference is negative, which I thought was pretty insightful. It'll work. You take the same thought process and you do it for heat exchangers. So we have a hot stream and we have a cold stream. It's not a hard question. Which way is the heat transfer inside the heat exchanger? From the hot to the cold. All right. Now you'll see this term. What is the blah, blah, blah of the adiabatic heat exchanger? That's like the, what is the, something of the gargantuan peewee. What? The gargantuan peewee? That isn't a mix of phrases. The adiabatic heat exchanger, meaning adiabatic, no heat transfer. Heat exchanger, the purpose is to transfer heat. But what do they mean if they say an adiabatic heat exchanger? To the environment. Everything is transferred within. So, what would be a good second law efficiency for this? Where is the exergy of the flow coming out of the what stream? Out of the hot stream or out of the cold stream? Which out of the hot stream. Okay? Does it all go? If I have 50 watts coming out of the hot stream, is there 50 watts going into the cold stream? Not really, because some could be destroyed because of irreversibilities, and there's a lot of irreversibilities in heat exchangers because there's heat transfer through a finite temperature difference. That's one of the big causes in addition to friction. So the exergetic efficiency of this heat exchanger would be, you came out of the hot stream, EF, which one is greater? EF2 or EF1, the hot stream? EF1 is greater. EF2 is less. I like working with positive entities. So this is what comes out of the hot stream, m dot h times EF. What goes into the cold stream? M dot C. I want a positive difference in flow exergy. Which one is greater? EF4 minus EF3. Do you see that would be a decent? That's a very good definition of exergetic efficiency. This would be a heat exchanger, which is a counterflow heat exchanger where they're not mixing. The fluid streams are not mixing. There's one other heat exchanger where they mix. Notice that the hot comes in and the cold comes in, so the hot gets warm, it goes out warm, and the cold goes out warm. They come out at the same temperature. But you use the same idea. You say the exergetic efficiency of this heat exchanger is where is it coming out of? The m dot 1 times EF1 minus EF3. Where is it going to? M dot 2 times EF3 minus EF2. Do you see that? Thank you very much for your attention. No class Monday. See you Wednesday.